'Cause like a winter tonight, I thought I would always have light. The quick flash that you gave to me, so dark I could barely see. Looking
from wherever you are around the world, welcome and thank you for joining us. Today we are exploring time travel. So is this show in the present? In the past? In the future? Well, we're going to find out all about that with Dr. Charles Adler. He is a professor of physics at St. Mary's College of Maryland. So let's welcome Dr. Adler to the circle. How are you, Dr. Adler?
I'm doing well. Thank you for having me here.
This is an interesting topic. Like I said, the past is going right by us right now. 25 seconds ago has already passed since I said, welcome to the circle. But can we travel back? That's what I want to explore with you a little bit. But before we get into time travel and whether it's possible or not, I know physics professors and even philosophers have some difficulty sometimes defining what time is. What is time?
It's a good question. There's an old joke that goes that time is what keeps everything from happening at once. But the way physicists think about time is very similar to just another spatial dimension. In the theories about physics, the theories of relativity that talk about how time behaves, we treat time in some ways as if it were like space, except that a special kind of space in which you can only really go in one direction rather than, if you can go right or left, up or down, backwards or forwards. But again, in the theories of relativity, again, time only moves in one kind of direction. But the theory of relativity basically says that time and space are kind of deeply intertwined together. If, for example, time and space change in very strange ways if you start moving close to the speed of light. For example, if you're in a spacecraft and I see you whizzing by me at 90% of the speed of light, and you're in your spacecraft and you measure the spacecraft as being 100 feet long, I'm actually going to measure it as being only 43 feet long. And similarly, if you got a clock in your spacecraft and you watch the clock tick off 1 second on your clock, I'm going to see actually a little over 2 seconds go by on my clock as your spacecraft whizzes by because you're traveling close to the speed of light compared to me. So time and space are very deeply interrelated in physics. And so again, we kind of define time time and space are kind of very deeply intertwined in that way. It's why physicists talk about time as a fourth dimension, but as an extra dimension which doesn't quite work in the same way as the other three spatial dimensions do.
Yeah, it's kind of a hard thing to grasp because there's something about the atomic clock where actually gravity affects time. How does that work?
Well, it's a part of, again, Einstein's theory of relativity, his general theory of relativity, which basically states that time moves more slowly in deeper gravitational fields. For example, again, if you've got a clock on a spacecraft orbiting the Earth, in a satellite, for example, as the time that it measures as for the period of a day is going to be about, it's going to see clocks on Earth running a little bit, tiny bit more slowly than the clock on the spaceship, maybe 38 microseconds more slowly than on the Earth, 38 millionths of a second. So it's not very much, but it's enough to measure. We can measure it pretty easily because we have these very, very good atomic clocks that keep time really, really well. And it's also enough that if it weren't compensated for, the global positioning system wouldn't work at all. 38 microseconds means an offset distance because basically, because the speed of light is so big, 38 microseconds turns into a huge distance, many, many miles long. And so if you didn't compensate for that by basically changing the clocks that actually go aboard these satellites to run a little bit slower, the global positioning system, this multi-billion-dollar industry, wouldn't work at all. This is one of the things I find really kind of neat about modern physics, is that these very esoteric effects, the general theory of relativity that says that time slows down when you're in a deeper gravitational field, actually have real-world applications. Now, it's a tiny amount for Earth. It's only 38 microseconds per day if you're on a spacecraft as opposed to on the surface of the Earth. That gets really strong if you're near a very strongly gravitating object like a neutron star or a black hole. For example, in the recent movie Interstellar, we have astronauts who are exploring a planet which is orbiting a black hole, orbiting very close to a black hole, and they come down from a spacecraft which is further away from it. And because they're deeper in the gravitational field of the black hole, they spend about an hour on the planet, whereas 10 years go by on the spacecraft. And that's really neat. And again, it's actually pretty accurate because they had a very good physicist, Kip Thorne from Caltech, consulting with them to actually go through the mathematics and make sure what they were saying was accurate. And it gets so extreme that if you were if I were in a spacecraft falling into a black hole and you were standing outside, again, watching me, you would see my clocks run slower and slower and slower as they approached what we call the event horizon of the black hole, the part of the black hole where nothing can get out of once something passes through there.
Crossing the Rubicon?
What was that?
Kind of like crossing the Rubicon?
Yeah, crossing the Rubicon. But you'd actually never see me cross it. My clocks would run slower and slower and slower, and they would eventually kind of freeze once I actually kind of got at the event, once you keep on slowing down, never quite hit the event horizon from your point of view. What's weird is that from my point of view, I just go through there and go to the center of the black hole and be, crushed to death by the black hole, by the black hole, the singularity inside the black hole, the huge gravity inside the black hole. But you would never quite see it happening because from your perspective, my clocks would keep on running slower and slower and slower and slower and slower and never quite reach there. And it's one of those amazing predictions of the theory of relativity that, as far as we can tell, actually, is really true. But again, it's just really very strange from the ordinary viewpoint.
Yeah, it really is. And is it safe to say then, you said the more gravitational pull, the slower the time. So would I be like living in dog years if I go to the moon where there's very little gravity?
Yeah, it's dog microseconds maybe. It's a tiny little effect. I mean, if you go to if you were on the moon, you'd maybe, let me think about this for a second. You would probably live about a millisecond longer, 1/1000th of a second longer over the course of your entire life than if you were living on the surface of the Earth. I guess that'd be good. Less. Other way around. Sorry, you'd be living a microsecond longer on Earth than on the moon. If you really want to get these very strong effects, you have to go to a really strong gravitational source like a black hole.
So that could be the fountain of youth.
Exactly, or at least, you wouldn't see it that way. You just live your normal life. It's just that billions of years would go by on Earth while you stayed near the surface of the black hole. You could use it as a time machine into the far distant future.
Now, I've talked to other physics professors as well, and I asked them about time travel. That's what we're going to talk about today a little bit. And they have a hard time going that way, going back in time. They said we can go from this point forward. So let's delve into time travel. What can we do, or what's possible of doing, I guess?
Well, going forward, like I just said, is possible. If you can find yourself a black hole, or if you can travel really, really close to the speed of light, then billions of years may go. If you can travel, then many years may go by as you're whizzing around the universe very close to the speed of light, while very little time passes for you on the spacecraft or sitting near the surface of the black hole. Whether or not you could actually go backwards in time is a very good question. I'm not going to say it's impossible to do. From what we know about physics, most of the laws of physics seem to imply that it's not possible to do, but there may be a little bit of wiggle room, again, in this general theory of relativity that Einstein created. The issue has to do with a couple of different things. Number one, going backwards in time is always equivalent to traveling faster than the speed of light. Traveling faster than the speed of light always implies going backwards in time and vice versa. And whether or not one could effectively travel faster than the speed of light, there seem to be some very highly theoretical solutions to the equations of the general theory of relativity and Einstein's theory of gravity, which might allow either faster than light travel or traveling backwards in time, but no one knows whether or not they are what physicists call physical solutions. That is to say, whether they are solutions which would be actually achievable in the real universe. They seem to imply the need for very special kinds of matter, and energy, which are not normally found, which are very different than the types of matter and energy that we're really accustomed to. So this is one of these situations where 99.9% of what physics says it's probably not possible, but there's this 0.01% of stuff which says, well, maybe it might be possible.
Well, now, isn't there I may be completely wrong here, but isn't the wormhole like a shortcut to that?
Yeah, that's the wormhole solution. Wormhole solutions are wormhole solutions of the general theory of relativity are the best possible way that people know about to actually either do faster than light travel or time travel. And the solutions, again, the tricky part is that when you look at wormhole solutions, you have to look somewhat beyond the general theory of relativity. You have to look beyond Einstein's theory. You have to actually combine them with the laws of what are called quantum mechanics, basically the fundamental theory of how everything works on a very microscopic scale, to figure out whether or not these solutions are possible. And the one problem is that no one has a great combination. One of the big unsolved areas in physics is actually how to combine Einstein's theory of gravity with the theory of quantum mechanics. And the theories of quantum mechanics, it's one of those questions which is kind of being debated. Again, the physicist I mentioned before, Kip Thorne, did a lot of pioneering work back in the 1990s about whether these solutions were possible or not. And the best he could come up with, and to my knowledge, the best that anyone's been able to come up with yet, is that, well, maybe, because he was able, there seemed to be what the quantum mechanics seems to predict, maybe, is that if you tried to turn a wormhole into a time machine, then it might destroy itself by what are called quantum fluctuations, because the energy would get so large inside of it that it would basically rip itself apart. But it's not clear that that's really what would happen. And again, the mathematics gets very complicated to the point where people like Kip Thorne and Steve Hawking and really big shots like that argue a lot over whether over what in fact the mathematics implies. So I'd say the answer is not decided yet.
Hi, welcome to Adelante. This is Adelante Recovery, and my name is Yvette Kuglin, and I'm part of the staff.
Adelante Recovery Center has helped people in dual diagnosis for 5 years. We accept most PPO insurances and provide luxury accommodations and 24-hour support. To speak with an admissions counselor, call 1-888-242-4450.
A lot of time we don't even know what's wrong with us, and sometimes we need to get away to figure that out. So if you want to go for a little retreat out in Corona Del Mar, which is a confidential location, we're here to help. So we're only a phone call away. Thank you.
Now, I think I can't remember if it was Brian Greene or not, but if it's not, well, I don't want to give him responsibility for this. Now, to explain to the audience the wormhole, I know we have a picture here of the wormhole, but time has looked like a fabric, right? A piece of fabric.
Mm-hmm. Space-time looks like a fabric, yes. Space-time.
The wormhole is kind of connecting one point to another, and it almost looks like an arch or an arc of a subway, if you want to look at it that way, I guess.
That's exactly right, yes.
Okay.
Or a tunnel, basically connecting the 2 points. If you read Madeleine L'Engle's book, A Wrinkle in Time, a long, long time ago, she talked about basically this idea of kind of folding space together.
That's right.
And then, moving from one point in space to the other point in space through. And the wormhole is what basically would allow you to move from one point in space to the other point in space in this folded space-time. So it's kind of like a tunnel between two very distant points in space-time. And again, if space-time is folded up like that, which no one really knows whether it is or not, but if it were, you could then just go very easily through the wormhole from one point in space-time to the other point in space-time. And so it's very much like a bridge between one point in space-time and the other point in space-time.
All right.
And And what people know about them is that they are in fact possible solutions of the general theory of relativity. They do are solutions mathematically. The tricky part is whether or not they would actually, whether or not they're stable, whether or not they would destroy themselves if you ever tried to create one.
So let's take this wild leap. Let's say if we could travel back in time.
Mm-hmm.
What does Dr. Adler think would happen? Let's say I go back in time and we incarcerate Hitler, for instance. Does that affect history? Can we even do that, you think, if we did? If we physically found our way to be able to get back in time, can we alter history, you think?
There are a couple of different viewpoints on that. My own personal viewpoint is probably not. The tricky part about that is that we like to think that there's this thing in physics called causality that basically affects, the sequence of events doesn't get disturbed. That basically, if you start something in motion, then it keeps on, having these effects as they keep on going down. And if you had time travel, if you were to disturb causality, and the most famous example of this is the grandfather paradox, where, for example, you'd go backwards in time and you'd basically kill your grandfather before your father was born. Well, the problem is then, who went backwards in time to kill your grandfather? Because you're not born then. And so then, is your grandfather then are you then alive or dead to go back, and there's this basically seeming paradox that gets created if you actually go back and do that.
I got to take a Tylenol. Hold on for a second.
The issue is that if time machines exist, then you have to ask, do you still have causality in physics? And it's a big problem. If you don't have causality in physics, then you basically have to reinvent physics from the ground up to create a physics without this sort of causality. We can actually have multiple things happening all at the same time. Now, there is actually one viewpoint of physics that might allow this. It's what's called the multiple worlds interpretation of quantum mechanics. Which was put together back in the 1950s by a physicist named Everett. And he put together this idea, quantum mechanics, again, is a very strange theory. Instead of particles basically moving along very well-defined trajectories, it has this idea that the particle trajectory is kind of fuzzy, as if it's in many places at once. Whatever it said was that one interpretation of this is that when a particle moves, it basically chooses every possible different way of moving, every possible different trajectory at once, but each of those trajectories is in a different universe that splits off from each other. So that there are many, many, many universes all splitting off from each other at the same time. Every instant in time, this is basically happening. And this is why quantum mechanics behaves the way it does. And so a physics without causality, a physics with time machines where you could actually do things like killing your grandfather, might be allowable in this vision of this sort of multiple worlds interpretation of quantum mechanics, where basically things keep on splitting off. Because in one possible multiple world, your grandfather dies and you're not born. In another one, he's alive and you were born. But the splitting off basically might allow for both possibilities to happen.
How seriously is that theory taken?
Very seriously.
Really?
Not the time machine part necessarily.
No, the multiple universes?
The multiple universes is taken very seriously. I don't know if it's it's whatever it showed back in the 1950s and what people have elaborated on since then was that it's mathematically consistent, at least, with our standard views of quantum mechanics. Whether it's correct is a very difficult question to answer because no one can think of a very good experiment to figure out whether it's correct or not. You can't kind of wander over into one of the alternate universes, or at least no one's figured out a way of wandering over into one of the other worlds that's allowed by this hypothesis to test out whether they're really there. But the mathematical predictions that it makes are, at least on first glance, identical to the ones that more standard theories of quantum mechanics would make.
So Dr.
Yes,
Adler
they
could
take it
have...
very seriously.
You could have already figured this out in another universe.
Yeah.
So let me ask you this. We got the causality. We have a few minutes left here, but you said the principle of causality is important for the past to be able to influence it for the future. But we also discussed it was easier to time travel in the future. So if I send a text to my wife that I shouldn't have, am I able to go forward and erase that text?
Only if you get to it before she can.
It's a light speed, huh?
Yeah.
All right. So we talked about that. Last question before we get to your fastball question. Last question. What are brains? I was reading a book on this. I can't remember the author's name. Forgive me for that. But she had a book on brains, B-R-A-N-E-S.
Right. Brains are a mathematical idea of how the universe, of basically the structure of space and time. They come out of what is called string theory. String theory is a theory that a number of physicists like as being kind of the ultimate theory of everything. And the fundamental idea there is that, again, matter is made up of, in a very, very, very elementary sense, things that basically act like vibrating strings, like a vibrating violin string under tension. We can explain elementary particles using those. Brains are an elaboration of that, in which instead of having, as best I understand it, I should say, I'm not an expert on brain theory, but as best I understand it, brains are essentially an idea that instead of strings, you might actually have these things as sheets. And the weird thing, and again, the thing about these strings is that the strings are weird in that they live in this odd sort of 11-dimensional space.
11?
11, yes, 11
Wow.
10-dimensional space. Brains, I think, live in the 11 dimensions, but I don't take my word for that one, because again, I'm not an expert on the theory, but so we don't, and again, this is a very, very weird theory, because we live in a 4-dimensional space-time, where at least we see 3 space dimensions and we experience 1 time dimension. And the other 7 dimensions are somehow rolled up, compactified is the physics term for it, into these tiny little spaces, into these tiny little volumes. And again, no one's entirely clear why they would be compactified like that. There's some people who have kind of ideas about why they would do this, but the idea is they're rolled up so tightly that we actually can't experience them or see them. We can't see the other dimensions. And people who are critical of string theory basically pointed this out as one of the big problems with string theory. I'm a string theory agnostic, I will say, because I don't know enough about the really higher branches of mathematics to really be able to weigh in with the judgment. But those are the general ideas of it. And again, a brain is just kind of a brain is an extension of the idea of a string, but into a sheet rather than just a string.
Well, I'm a physics agnostic, so. Let me ask you this. We've never done this before. It's the first time we're going to do it today. One of the guests asked me to ask a physics professor that I had on. He had a theory. He wrote a book on it called The Omniverse. His theory was the point of singularity was a white hole that blew out everything. Kind of like spewed it out.
The Big Bang. You're talking about the Big Bang?
Yeah, but what he did was that he had one white hole, and he said it's compared to a baseball in a parking lot. So we'll say, for my sake, I'm over here in California. Angel Stadium is here. You have the parking lot. Our singularity is just one baseball in this large parking lot. What do you think about that theory?
I don't entirely know what it means, I guess, is the question. Is that when you're talking, is he saying that there might be other like universes, other
Yes.
Big Bangs happening elsewhere, basically?
Yes.
In weird versions of space. It's a good theory, and there are actually physicists who think that actually might be true. One of the possibilities is that, again, this is distinct from the vision of alternate universes that I was talking about a little bit before, but one possible view of our universe is that it's actually not the only universe, that there are actually continually other universes being born very similar to ours, possibly with slightly different values of things like the speed of light or the charge in the electron or the force of gravity. Other things like that might be having slightly different values for it. And that might, people like that idea in some ways because it does solve one of the big problems in physics, which is why our universe has these particular values for the speed of light or the gravitational forces or things like that. And the answer might be, well, there might be no fundamental reason why they have them, because if universes are being born all the time that have slightly different values, the values we got might be basically at random. We've gotten them at random, and there's no fundamental reason why we got these particular values, because other universes might have different values.
That's a good answer. I think he'll appreciate that. All right, you ready for your fastball question, Dr. Adler?
Sure.
All right, so Dr. Adler, let's say we finally discovered it. St. Mary's College of Maryland is totally ecstatic. Dr. Adler's figured out time travel. They can't believe it. So now they're trying to figure out, now Dr. Adler has a choice. He comes at home, he's sitting down, he realizes, well, wait a minute, I can go back in history and go on a date with anybody I want to from history. Who would Dr. Adler go out with?
Leaving my wife out, assuming that this is an alternate universe in which I am not married and happily married. The father.
Well, she gave you a time travel pass, I think.
Okay, yes. I've always been fascinated by Cleopatra.
Oh.
Kind of an obvious answer, I know, but Cleopatra, the last pharaoh of Egypt, has always held a fascination for me because she's a really interesting historical character. She met and married two of the greatest, two of the great figures of the ancient world, Julius Caesar and Mark Antony, and was in many ways at least their equal, possibly even a better statesman and politician than Mark Antony was, and was able, she ultimately failed in what she was trying to do, but she was a really great, I think that she was a really great stateswoman, a really great leader of Egypt at that time, and really very, very interesting person. She spoke something like 7 different languages, was extraordinarily well read, beautiful by all accounts, and so really kind of interesting person. So someone I would very definitely like to meet. Now, I'm not sure I can compete with either Mark Antony or Julius Caesar, but still.
Yeah, nothing didn't happen. Good ending for them. Was not a good ending for them. I mean,
no.
Dr. Adler, thank you so much for being on the show. Oh, I don't want to leave you. That's right. I did not want to leave you alone on the fastball question. I was going to tell you who I was going to pick. I was going to pick Lady Godiva. Maybe it's based on the mythology. I don't know. Sounds appealing to me. Thank you so much again, Dr. Adler, for being on the show.
Thank you so much for having me here.
Actually, before we go, where do we get a hold of you, Dr. Adler, if you want more information?
Well, you can find my contact information at the St. Mary's College website and also on my blog, Wizards, Aliens, Starships, and More on WordPress. You can also find information about me and my book, Wizards, Aliens, and Starships, on Amazon and on the Princeton University Press webpage for it.
Wizards, Aliens, and Starships. Thank you again, Dr. Adler. Thank you, everyone, for joining us. One thing before I leave, people ask me sometimes, well, how does this relate to psychology? Well, I'm going to tell you really quickly. Our global perspective, even our perspective or view of life, influences how we perceive things. That affects our attitudes. It affects our values and judgments, which then in turn affects our decision making. That's how. So remember, our motto is simple. Wherever there's psychology involved, even in the past, present, or future, we are there. See you next time, everyone.